I'm the founder of TuringDB.ai, and basically today I'm going to explain what is exactly TuringDB, why we built it. So today I am with my co-founder Adam, who is just behind the camera. Hi Adam.
Hello.
Basically, why did we build TuringDB? So if you don't know already, TuringDB is a new graph database that we built from scratch in C++, if you know what it is. For building basically the fastest graph database in the world, because we had some experiences in our past lives with graphs. If you don't know the history of our company, basically we started as Turing Biosystems in our previous life to basically build graphs for biology and make sense of the enormous complexity of what's going on in the human body, in human biology. And so we used what was available on the market, like everybody. We used Neo4j, notably. Adam here used a lot Neo4j in his life. It was the source of his pain, right?
Absolutely, yeah.
Yeah, and so like it's not really a secret in the bio industry, but like everybody, we saw the shortcomings of Neo4j. Let's say we saw that when you go beyond about 1 million nodes, 1 million edges on either a typical computer or let's say a typical Linux server that you can get at a reasonable price, it started to be really slow when typically in health or biology application you need to go beyond 3-4 hops. You need to go 10 hops, 100 hops down the line because you are investigating complex biology phenomena that may be linked through hundreds of hops down the line. To the things that you want to investigate. And in a lot of industrial and scientific applications that we have seen, it seems to be the case whenever you do something which is more than a toy graph with a few nodes, essentially. And so we wanted basically just to have something that works. And basically I had a lot of experience to build this kind of graph representations in a high performance way in my past lives. For a variety of engineering applications, and notably in semiconductor to represent really big chips, GPUs and CPUs, which are made of millions and millions of nodes and wires inside, so an enormous complexity, and obviously to build the latest GPUs to represent the graph of components inside, people don't use Neo4j for this. Everybody kind of makes their own homegrown graph representation from scratch on the side in C++ or sometimes Rust these days. And so I was like, okay, well, let's use these good principles that we know in the semiconductor industry, that we know in all these critical industries that need high performance. And so that's how we went to build our own high performance graph database from scratch, basically.
Maybe we can go through a few questions we had also from different people in the last few days and also explain some of the critical technical concepts behind TuringDB, like I think why we are so fast, what do we mean by high performance as well. Maybe one thing we can start with is one of the core concepts in the design of the graph database, which is the data parts.
Yeah.
Because it impacts so many things like speed, how we use memory systems, the versioning, the native Git-like versioning, we have all those things, snapshot isolation. Could you explain in a semi-technical way, let's say, those data parts, please?
Yeah, sure. So the idea of data parts is maybe one of the things that are not typical. It's not part of the, let's say, typical database ideas or the things that we know that we can hear in other database products or in database research. So basically, where does it come from? What's the issue with graphs, and why graph databases tend to have a reputation for being slow or for being really difficult to be made fast, okay? So the first thing to notice is that if you have a graph, so a graph is what is nodes, okay, which are related by a bunch of relationships or rows on my whiteboard. So I can have a bunch of nodes like this, okay, So I have nothing on my nodes and my edges yet, but usually the typical example is the knows Will and James and Sally and John and all these guys that know each other. So I don't know, I can have a node called John, for example, that knows Sally, and he also knows Michael. And then there is a bunch of other people, so like James, Isabel, Mary, and Peter. And so this is a graph, and the classical way to make a graph database out of this is like the Neo4j way, where Neo4j is implemented in Java, and in any kind of object-oriented language like Java, technically, we will have basically an object, a Java object, per node and per edge, in the most basic way. Obviously, there are many other things, notably for properties, but at least in Neo4j, there is an object, a Java object, for each and every node in my graph, and for each and every edge. Okay, so you know, a Java object is something that's an instance of a class where I have essentially class node, blah blah blah, and when they create the node John in the graph, you ultimately, when Neo4j processes your create query, in the end, at some point, what it does is that it does a new node object, sets the name to John, and then when it goes to Sally, create a new edge object that will be connected to John and Sally. So all these guys are different objects that somehow live in the memory of my server, live independently in the memory of my computer on which Neo4j runs. So when basically Neo4j will execute your match queries to go from one node to another and to basically explore your graph, to be like, okay, who are the people that John knows directly, you know? So who John knows directly? Well, it's just Sally and Michael, right? Mm-hmm. So that's what we call a one-hop query. So I can write something like this in Cypher, in Neo4j query language, which would be match P, which is, let's say, a person in my graph schema, and say name John, a row somebody else that I will call N. Not very original here, but then I can return all the nodes N, basically, that are directly related to John. So, to not go on the wall and go out of the whiteboard, obviously I omitted to say that I only want people that John knows. Okay, so I could have put that on my edge. But anyway, here, this is basically a match query that I can then run in Neo4j on my graph. And what it will do is that it will basically start to locate what is the person P that satisfies my constraint here, so John, and it will try to retrieve each and every object, each and every entity in my graph related to John. So first it will go through that edge object, and then to the Java objects that represent Sally, and the objects that represent Michael in memory, and so on and so forth, if I had another graph with possibly thousands of people. And so all these guys are potentially stored anywhere in memory. They are different objects. I don't know where they are. So in general, for modern computers, jumping from one memory place to another is really, really expensive, okay? Because modern computers, if you don't know, they have been crazily optimized for basically like places that are stored next to each other, because Neo4j and others use like different Java objects that can be stored anywhere in memory, basically for all the nodes and edges of my graph. Basically, the computer spends, like the CPU spends a lot of time to retrieve all of these objects from potentially anywhere in memory. And so that's why traversing a lot of hops still here already for one hop, but if we imagine to do this 10 times, 100 times, 1,000 times, it becomes very, very slow if the graph or the number of nodes becomes really, really big. So I don't know, Adam, if it makes sense from your point of view.
Yeah, I think it makes absolute sense. I would have a question though, so for example, let's say when you do that deep traversal, that was one of my big problems, you use multi-hop things. Let's say we go beyond this full connection, James knows that ghost person there that doesn't have a name.
Oh, yeah.
This person, we can call it Ghost. Yeah. And then that Ghost, knows Henry, and Henry knows Elizabeth,
Yeah.
And so basically, let's say you are going quite deep in this number of hops, okay? What happens, is this why those deep hop breaks? Because they are so scattered across memory that you just have to wait so many back and forth, or it's more complex than that?
So it's one reason, the fact that it's scattered all around memory doesn't help, because you don't reap the benefits of all of those things that we have in the chips, really, is that all the optimizations that are baked in when things are close together.
Yeah.
So this is why the first intuition, let's say, is as a person from the semiconductor industry, I could totally imagine benefits of the order of magnitude of being 10 times or 100 times faster or more if things would be clustered together, okay? Yeah. And then the second reason is it's even worse, because there is an exponential effect going on here, because if we do all the nodes related to John in one hop, there is 2 here, but then if we go more than one hop, we also get all the nodes that are related to Sally. Yeah, so it has a multiplicative effect, a combinatorial effect, where if it was a larger graph, then it would go all the guys that are potentially related to Mary up here, and so on. So it explodes very quickly, yeah. And so this combinatorial explosion amplifies kind of this phenomenon.
Okay. And so I remember what we talked about a little while ago about this concept in databases of volcano model versus more newer research around column-oriented. So could you explain to us a bit that aspect here, because I guess that's also comes into play with that memory optimization.
Yes, exactly. So the conclusions that we can draw from this is that looking up a bunch of objects or entities that are scattered all around the place in the memory of my computer, God's nowhere really, I don't know where they are, it's really, really bad for modern computers. And so it's also really, really bad in general for a database to do things bit by bit, entity by entity. Like if I am doing multiple hops, to be like, okay, there is one neighbor of John here, then there is another neighbor of John here, then I need to do a second hop. So what are all the neighbors of that guy, and so on and so on. And so I am computing the results of my query bit by bit, node by node, edge by edge. Okay, so like all the database researchers basically will probably scream at me, but in a very quick way, this is what is called the volcano model in database research and in query processing more precisely, which is the name of a paper from quite some time ago, which describes basically how most databases today work, how most query processing works today, which is you basically process everything bit by bit. So you start from one starting point, John, and then you have a get neighbor operation, which gives you Sally, and then you repeat that same get neighbor operation to get another neighbor, which is Michael. And then if you want another hop, you continue the same operation, but one by one. And so obviously this is fitting very well in that world where everything can be related to anything and placed anywhere, scattered all around the place. Okay? And so if the problem is to be scattered all around the place, can we very naturally try to collect as much stuff as we can, really packed tightly together in the same place? Can we cluster as much as we can the nodes and edges in the same place? And so, in a more general way, in modern databases and in modern database research, this is what people have been trying to do, not for graphs, but for, classical relational databases where what I am looking at and what I am traversing is just rows in a table, okay? And so basically just a little parenthesis, if you have a classical relational database and you are just traversing a table to see, for example, it could also be the friends of John, but I don't know, maybe can you find me the customers that have orders greater than £100? You would be traversing all the rows of your customers table, and actually only one column would contain the price that you are interested in. So you would traverse, okay, there is a first name, then there is a last name, then there is the address and whatever things you put in it, okay? So, in fact, the things that you need is only that price column with respect to what you are interested in to see the orders greater than £100. And so, people have been thinking about this, about ways to, can I cluster what I need together? And so what they have been coming up with is to organize datas into columns, which are basically big arrays of data put one after the other, instead of being row by row as I just explained. So in the case of customers and orders and prices, you would have one big array of prices, one big column of prices, one big column of first names, one big column of addresses, and so on and so forth. So when you are interested only in prices, basically as a database engine, you would only iterate over the prices only. And so you would only be iterating over an array of prices, and each price would be exactly next to each other in the memory of the computer. And so by modern computer hardware, we know that things, when they are really next to each other in memory, this is being very fast. And so basically this is what modern database research has been about in classical relational databases. Now, to our knowledge, this has not basically been fully realized or fully utilized in the context of graph databases. In the world of graph databases, remember, we are still in the in the world of Neo4j, and if we look at memgraph or others I won't cite, it's kind of the same with some sophistications around the edges, of course, but kind of the same in the sense that we assume that graphs can be connected in an arbitrary way, and so all the nodes and edges are in their own little object with their own little life, stored goes nowhere in memory, completely scattered all over the place. And so people have not been fully appreciating this idea of column orientation in graph databases. So how can we leverage it? And that's basically what we are doing with TuringDB. It's basically, you can guess it very simply, probably, it's to put all my nodes and all my edges together first in very big columns, okay, in very big arrays. The way we will primarily store the nodes and edges of my graph will be in very big array of nodes and edges, so that when I want to traverse all the nodes of the graph, it's obviously very fast, but if I want the neighbors of somebody, and we'll see how if my edges are clustered together in an intelligent way, well, I can just be like, okay, here are all the edges of John, going out of John, to Sally and Michael. And so all these guys are next to each other in memory, and so my database can really go over them really quickly. Okay? And so now I end up into the good case of everything is clustered together, everything is tight together in memory, and this is the ideal case for modern CPUs and modern semiconductors.
So basically, that has to mean, like, with the analytics, for example, if you start exploring a graph from a specific node, because we cluster those in a clever way, we can go a lot faster through the graphs as well, isn't it? Because if you are close to each other, you can just, each hop has a much lower computational cost, or am I wrong?
Exactly. So the computational cost, the speed
Yeah.
is a lot faster. And that's how we can sometimes achieve 100x or 200x improvements. And frankly, when we go 10 hops, like in many cases, like when you have just 1 million edges, 1 million nodes in Neo4j, people say, why will you go more than 4 hops? You know, like meaning, are you crazy sometimes? And with this kind of approach, we can go to 10 hops, obviously, very, very simply, because in many industrial applications, just 4 hops mean nearly nothing for anything really serious. And so we can easily go 10 hops, 100 hops, and the more hops we go, the more speed up we achieve, actually, because of that combinatorial effect I explained earlier.
Yeah. Fair, yeah, exactly.
Okay, so that's how, due to this initial design of let's put everything together in a contiguous way, that's how we can achieve speed ups of basically 100x or 1000x when you have really a lot of hops.
Yeah, okay, that's great. And is there like, because you mentioned, for example, let's say, they infer, like one of our hypotheses with the graph here and the design is that graphs are not arbitrarily connected. There is certain logic in a graph, in general, when you analyze a graph, unless in some categories of graphs. Does it mean, like, is there like a potential downside comparatively to those graph databases that do just take into account, you know, that everything can be connected anywhere?
So not really, because so let's say there is cases where we will be even better compared to others.
Okay.
Basically, it's the way we lay out edges. We cluster close together edges of nodes that are connected, obviously. So that means that here we have all the edges of John, and then all the edges of Sally, and then all the edges of Michael. So where you will win even more, let's say, will be cases where, obviously where you will win depends on actually where you start in the graph, but basically in graphs where you have a lot of arity, so a lot of things that are branching out of a given node. You know, people that are well known or places that are connected to a lot of stuff. It means that you will have everything together, and if you are in your analysis interested by neighbors that somehow stay kind of close together in the same area, you will win more.
Yeah.
But in any case, we will be never slower than the other approach that anyway scatters everything everywhere in memory arbitrarily.
Fair enough. Okay, fantastic. So I think, yeah, we covered a lot of concepts around the speed, why the GraphDB is faster. Is there anything you would like, because we are reaching basically the 30 minutes, so I think we can tease some future stuff around the versioning.
We can keep fun for later.
Exactly, like more things for later, plenty of exciting stuff to share. And of course, we have stuff in the documentation too that people can read in their own time. But here, is there anything else in your mind that you would like to share to explain like that aspect of exceptional difference? Because I think some cases people are very surprised that it's actually that kind of difference of speed. So there's the design, of course, and that's memory space. Is there any key concept you would like to share at the end to finish up the story?
Yeah, so that story of being contiguous as much as we can and storing all the nodes and edges together, the idea of being contiguous in general, goes beyond just the primary storage of nodes and edges. It's also in our query processing itself. So I'm just going to erase my graphs because I have no more space on the whiteboard. But basically, you know, when you write a Cypher query and you go from P person, here I won't give any kind of property restrictions, but let's say I want to go 3 hops, okay, over 3 linked persons, P, N, and M, okay. I can actually restrict P name to be John so that I can be sure to start from somewhere well known. Okay, P and M. Okay, so the way we interpret such a query, the way we execute such a query in the engine is by building a query pipeline. So a query pipeline is very simply the sequence of operations the engine will execute. So what it will do, basically, well, it's kind of nearly already said in the query itself, right? It needs to scan all the persons, all the nodes with the label person. So scan nodes with the label person, then feed that result into expanding all the edges of P person, which is in my case John, and then doing another expansion for M. And so let's say this is N, let's say this is M, and actually I'm only interested in persons here. So I'm just noting this here to expand only edges that go to persons, okay? And here I can return my result. And so this is kind of what the engine does to process your query. And okay, remember what I just said about earlier, the difference between the Volcano model and the column execution recently in modern relational databases. Okay, one way to execute this would be, okay, I'm starting from one node, which is John, this is very fair, and then expand edges. But expand edges, I would do it bit by bit. I would say, okay, then there is Sally, and then Sally has herself, she also has friends. For example, there is Peter. Okay, so I have a first result, which is John, Sally, Peter. Okay, I can send it. And then to get another result line, I would have to go back to, okay, so he has no more friends, that's okay. Poor girl, but that's okay. Then I would need to go to the other friends of John's, and there is Michael, and same thing for Michael. What are the friends of Michael, and so on and so forth. So propagating each individual entity through that query pipeline one by one. Yeah. This is the Volcano idea, well known in every database, such as PostgreSQL, for example, everybody. And so a way to get more performance is to, instead of going one node per node, we can treat many entities at a time by propagating columns of data again through these operations instead of individual nodes and individual edges. So that first I have my first person, which is John I'm starting with. Okay, and then now I take all the friends of John in one go. So that was Sally and Michael. If my graph was very big, obviously I could have thousands of people in one go. Yeah. And then I am transforming these thousands of people in one go to expand their edges in another hop.
That also explains why it goes also really well to highly connected nodes.
Exactly.
That you can explore really fast despite the combinatorial explosion.
Exactly. That's how we can regain somehow performance out of the combinatorial explosion, because we go by big chunks of data at a time. And again, big chunks of data that are in arrays, really nice, tightly packed together at the same place. Everybody is happy, the computer is happy, and so this is very fast.
Fantastic.
So this is the idea of column execution, column-oriented execution, also by transforming big data or filtering big chunks of data at a time. And so this is also what some people call a streaming query processing pipeline. And this is, we are one of the only people basically to do it in the graph database world. And this is one of the key aspects of our performance.
Brilliant. All right. Well, I think it's stuff that we are sharing a bit in our documentation. We'll share also in our upcoming white paper. Yeah. And I hope like some nerds like us will enjoy enjoy that. We enjoy it. Yeah. We had fun doing that. So I think it's okay. So thank you, Remy. I will say goodbye.
Thank you.
Surprise. Bye bye. Thank you. And we'll
see you next time.
Let us know if you have any questions. See you next time. Bye bye, guys and ladies.